So now I would like to welcome our next speaker, Bogdan Engelina from Transylvania University of Brasov, Romania. The title of his talk is Covers of Fractal Interpolation Surfaces with Families of Octahedrons. Over to you, Bogdan.
Okay, thank you. So I will introduce a bit of the notion. The structure of the talk is as follows. I will first
If
start
possible, can
with,
you make it full screen? Sorry.
it's not full screen. On my screen is
No.
full. Wait a second, just let me, okay. Let me see because, okay, like this is full screen.
Yes, yes, yes. Okay, okay. Now full.
Okay. Okay, thank you. Let me move it here. Okay. So, the structure of my talk is as follows. I will start by introducing a bit of the context in which we are working on, so the theory of iterated function systems we are working with, and also what we mean by coverings. And after that, a small, uh, let's say, introduction into fractal interpolation surfaces and how we can cover them. My talk will end with some examples of this structure, but we'll see in a bit. So, the first thing we have is the following definition. We are working in the context of classical iterated function systems. Uh, so, we have a pair composed of a complete metric space and a family of functions, a finite family of functions, uh, indexed by some indices I from the set I. The space should be complete, and the functions we consider are Banach contractions in with respect to the metric D. To this kind of system, we attach an operator that works on the compact subsets of X and takes compact subsets to compact subsets of X and is defined as the union of the images over any compact subset of the functions from the family. So, this operator is usually called the Hutchinson operator, associated with the system S, and we will have to see in our context of fractal interpolation surfaces what is the practically this entire structure in which we work with. The big theorem that the famous theorem of Hutchinson is that in this context, for an iterated function system where the functions are contractions, the fractal operator is in respect with the Hausdorff-Pompeiu metric on the compact subsets of X, a Banach contractions. And since it is a Banach contractions and this space, it can be shown that it is complete. It has a unique fixed point, which we usually denote by AS, and we call it the attractor of S. Since we can recover this set by iterating the fractal operator over any compact subset, any arbitrary compact subsets. And by iteration, we get this attractor. So, one of the important aspects of working with iterated function systems involves the localization of the attractor. What I mean by that is that we should know where the attractor is without it being necessary to calculate the actual attractor, because from the computational perspective, it can be quite a challenging task in some cases. It depends on the number of functions we have in the system, and it can be quite hard to obtain exactly the attractor. So we want to find some approximations. Uh, in one of our previous papers, okay, so I think it's a bit too zoomed in. Okay, in one of our previous papers, we proposed such a method of constructing a finite collection of closed balls that contains the attractor, which from the mathematical point of view can be used in approximating the box counting dimension of the attractor, but also in the theory of localization, it is also useful because if we want to place the attractor somewhere in a 3D environment, we should know where it is before we generate it, or there are other aspects from this point of view. So, what we mean by localization, what we did in the paper mentioned in the previous slide, if we have an iterated function system uh, with n functions, and we consider some radiuses, rho I, that satisfy the following system of equations. So we have the Lipschitz constants of the functions, we have the maximum distances between the fixed points of each function and the maximum radiuses. We want to solve this system, but if we have a solution of this system, before we solve it, if we have a solution of the system, we can show that this solution lets us build a union of closed balls centered at each fixed points and having radiuses rho I that contains the attractor. So the main idea is with a minimal set of data, let's say, so only the fixed points of the functions and only the Lipschitz constants, we can find this covering set. Uh, in the paper, one of the problems is that to find a solution to the system, we had to reorder the functions with respect to their Lipschitz constants, which, again, if we have a lot of functions, this can be somehow computationally intensive. And the main idea is that we want to change this aspect so we do not have to reorder, or we can find somehow the radiuses in linear time. And also, there is also a slight problem regarding the Lipschitz constant that is in front of this parenthesis here, because for some functions it is easy to find the actual Lipschitz constant for the functions in the system. For other systems it can be quite difficult. So we want to see if we can replace this constant with something else. Uh, so in this presentation, I will present some results from the paper mentioned below, and we refine this method in the following ways. We replace the Lipschitz constants with some other contractive constants that are uh, greater than the Lipschitz constants, and we show that in this way, the previous result is still valid, so we still have a covering that contains the attractor, and by substituting the Lipschitz constants with these contractive constants, we also are able to find a solution only by finding the maximum value of the contractive constants and the second maximum value, which can be equal or not. So the main idea is the following. I'll just have some notation that we require in the following slides. So in what follows, we consider iterative function system that has exactly n functions. N should be greater than 2, because if we have n equal to 1, then we have just one function and it's not very interesting. By gamma I, we denote the fixed points of fi, and by m, we denote the maximum possible distance between the fixed points. So we take the distance between any two fixed points and we take the maximum of this kind of distance. And by CI, we understand some contractive constants that verify this inequality. I will jump a bit over the next notation because I do not require it right now, but I will come back to this. So we consider the new system, sigma, which has the unknowns rho 1 up to rho n, and consists of the following n equations. So we have rho I. This time we replaced the Lipschitz constant with some Ci, and it is multiplied to the maximum distance plus the maximum of these radiuses. So we will find somehow a solution of this system. The reasoning behind the result in the previous paper of the localization of Hutchinson-Barnsley fractals actually makes this result very similar in the aspect that the proof of the containment of the attractor is very similar. But we are able to find in a more efficient way the radiuses in this way, in this framework. So the attractor will be in the union of the balls centered at the fixed points and having radiuses rho I. Now, by denoting with I prime the index of the Ci constant, which has the maximum value between all the Ci's, and by I double prime the index different from I prime, such that we have the second maximum in Ci double prime, we can show that the following are solutions of the system with the following formulas. And this is important because now we have a closed algebraic formula for calculating the radiuses, so we can compute them very fast. There are some minor problems, let's say. The first one is that these contractive constants can be close to 1, depending on the system. So as you can see at the denominator, we have this difference. This makes it that if the constants are close to 1, these radiuses can be very big. And we'll see at the example part how this can happen. We also would like to have some way to make these radiuses smaller, because depending on the attractor, the balls can be very big, the covering can be very big, and we would like to make it closer to the attractor. Uh, I will talk a bit about this a bit later, but combining these results, the radiuses, and the previous result we mentioned that the attractor is contained, we can write it in the following way. So the attractor is contained in n-1 closed balls centered at the fixed points having this kind of radius, and another ball that is corresponding to the function with the greatest contractive constant, having a similar formula, but is just the radius is a bit different because it is multiplied by ci prime. So, how can we make it smaller? A well-known result is the following. So if we take the system, the iterative function system consisting of the same metric space, but now we take all the possible compositions of the functions from the initial system of p functions, then it can be shown that this system has the same attractor as the initial system. Now it has many more functions, but the contractive constant or the Lipschitz constant, depending on what we use, is getting closer and closer to zero, because when we multiply, then we have the contractive constant can be chosen as the product of the contractive constants of the previous functions. And if we look at this product, then this product is smaller than the maximum contractive constant raised to the power p. So this will, as p grows, this will go to 0. So applying the previous method of constructing the balls, we can find some other covering for this system that has the balls as small as we practically want by increasing the p. But with the, let's say, problem that as we increase p, also the number of balls grow. So it depends on what we want to do. Okay, and now this is a small introduction in with what we mean by covering and the idea of localization. Now I will present a bit about fractal interpolation surfaces. So the main idea is that Barnsley used the framework of iterated function systems to initiate the theory of fractal interpolation functions. And this method constructs continuous functions that interpolate some given data with and having some kind of fractal properties. So the main idea of Barnsley is that given a data set with n+1 points, then we can somehow construct a function that interpolates a continuous function that interpolates the points from the dataset, and the graph can be presented as the attractor of some kind of iterated function system. So this method is very well suited for modeling irregular and complex curves and surfaces, and there are many applications in computer graphics and in other sciences. From this idea, it is a natural generalization to work with fractal interpolation surfaces. So Masopust developed an approach of constructing fractal interpolation surfaces over triangular regions, but with the condition that the interpolation points on the boundary all lie on a common plane. Geronimo and Hardin propose some algorithms for generating the fractal interpolation surfaces over arbitrary polygonal regions without having the conditions on the boundary. But another notable contribution, which we will actually use in this presentation, is the one by Dalla, who constructed by varied fractal interpolation functions over domains in R2. This is the most natural generalization because it is very, very similar to the one done by Barnsley. And we will present the details of this in the following part. So, following Dalla, we have this idea. We take some interval I and some interval j, but this interval is given by the dataset we have. Now we are working with fractal surfaces. We are in R cubed, and we have the following the data points. So we have n x points, m y points, and for each pair corresponding to a point in the plane xy, we have a z point that is corresponding to the first two. So we take the interval AB to be just given by the smallest x and the biggest x coordinate, and CD to be the smallest y and the greatest y. With this data set, then Dalla shows that there exists a continuous function in a similar way to the result of Barnsley that interpolates the data from the dataset, and also its graph can be presented as the attractor of a iterated function system given by these functions fkl, which are constructed in the following way. So we have k between 1 and n, l between 1 and n, and the function fkl, which goes from our cross product of the intervals and r to the cross product of the intervals and r, and has the following form. So we have a linear term in the x coordinate, a linear term in the y coordinate, and in the z coordinate we have the additional, let's say, part that we have this xy term at the end. The coefficients from the definition of these functions can be chosen such that we have the following conditions. So in the Barnsley case, the main idea is that we want to take the big interval from x0 to xn on the axis to a small interval xk minus 1, xk, let's say. Uh, from the interval, if we go to surfaces, now we want to take the square. So the biggest square we can have, given by the biggest data points, then we want to take it to a small square corresponding to each intermediary point. So given these conditions that we take each corner of the square of the rectangle to each corner of the interior rectangle, then we can find all the coefficients besides the coefficient GKL, which is arbitrary and can be chosen in the interval 0, 1, and lets us also modify the surface because we can modify it as we want. This coefficient, we can modify it as we want. Okay, and the first problem is that if we want to build this system, then we have that FKL should be contractions. In the usual metric of R3, this is not usually true. So we want to find a metric that makes this a contraction. So this metric is given as the following by the following formula. So we have the difference between the x coordinates, the difference between the y coordinates, and we have some kind of scaling on the z coordinates, where this theta is chosen as the minimum value between the values theta 1 and theta 2 provided here, but with that depend on the coefficients. So depending on the system or the data set, we have to find these values. Now we will work with this metric, and we are interested to see what the closed balls with respect to rho look like. And by solving this kind of inequality for an arbitrary radius, we can show that the closed ball in this metric is an octahedron having the vertices given as by the following formulas. So having the center at the point x0, y0, z0, we move on each coordinate by r, and only z depends on r and also theta. So we are able to find how these closed balls look. And uh, what we require after this to apply our theory of localization, we also require that we know what the fixed points look like, which can be determined algebraically because we have the linear term in x and the linear term in y, so it is quite easy to find them. And also by replacing this in the z coordinate, we can find the fixed point for the z. Now we need to find the maximum distance between this kind of fixed points. We denote it by m. We do not have an actual formula for it, but it can be calculated computationally quite easily because we have the formulas uh, for the fixed points. So having this, it can be shown that for FKL, a contractive constant is the following, given by the following formula. So by choosing the maximum of these contractive constants and the second maximum, and which we again denote by prime for the maximum and double prime for the second maximum, uh, the theorem from the previous slides shows us that if we take r prime and r double prime like this, then we can show that the following, the graph of the interpolating function of the fractal interpolation surface, which we again saw that it is can be given as the attractor of the previously mentioned iterated function system, can be covered by these octahedrons having the fixed point at ykl and having the radiuses given by these formulas. So this set we will denote by CS, and we call it the covering of this graph. And based on the previous result that lets us do the compositions, then if we take FKL and do all the compositions for some P, for some natural P, then we can find another covering that should be closer to the attractor, to the graph of the fractal interpolation surface, for the graph of the fractal, for the function. This we will denote by CP. And by decreasing the P, then the octahedrons will become smaller and smaller. Now, for some examples, what we can see here, we take this example of x and y with 3 points and the corresponding 9 values of ZKL. So we have 9 points in total that need to be interpolated. And for the GKL given by this data from the table, then we can find that the fractal interpolation surface looks approximately something like this. So it has some kind of valley. Then, using the localization, we have the following visualizations for the coverings. What we can see in the first picture is that the fractal surface and the octahedrons are very far apart. So the octahedrons, because of the Lipschitz constant or the contractive constants that we calculated before, those are quite big for this example. And this means that the octahedrons will be very far away. And it's not very interesting for our localization idea because actually the surface is contained in all the octahedrons. But what we can do, we can look at the compositions. And this lets us make the octahedron smaller and smaller. And we can see that by taking a small number of steps, so like 9 steps, then for C3 the octahedrons are closer, for C5 closer but still a bit far away, but for C9, so taking compositions of length 9 of the functions, then the fractal interpolation surface is covered quite well by the octahedrons. Actually, maybe if I zoom in, we can still see between this black cloud the octahedrons. In the C7 picture, we can still see the vertices. It is a bit harder to see them in the C9 because of the dimensions. And another similar example, if we take now 4 points for x and y, and this means 16 points for the ZKL, so 16 points in the dataset total, then if we take the GKL given by this dataset, we can find that the surface looks like this. So this is more, has some, let's say, mountainous areas and also some valleys. And the same thing happens here, but the Lipschitz constants are a bit better. We can see that the surface is not contained in all the octahedrons, but is mostly in all of them. And by taking these the compositions, then we can make it smaller and smaller and actually approximate the surface by this octahedron family. So this is the main idea. I would like to point out the fact that everything in this construction is algebraically computational. So we do not have any kind of iterative concept. We use only the functions, and if we can find we found the formulas for the contractive constants and the fixed points, then we are able to construct this kind of covering only by using the points from the dataset, because the coefficients of the FKL functions can be calculated by some formulas only from the dataset. And since we have the coefficients, then we can find the value of theta, and by finding the value of theta, then we can find the value of the fixed point and the contractive constant that depends on theta. But we have all the data, and it can be all calculated on the computer. So this is the main idea. Thank you for your attention.
Thank you. Thank you so much, Bogdan. So now I would like to request to the audience if they have any question for the speaker. So if there is no question, let us thank the speaker. Thank you for the presentation.